Alrighty, guys, this is section 17.7, where we discuss one of the two crowning results of vector calculus, chapter 17. So this is a rather important theorem, Stokes' theorem, and 17.8 we'll discuss the divergence theorem. Both of these theorems actually kind of lay the groundwork for a lot of the world that we see around us. They're used throughout the study of physics everywhere, especially in electromagnetism. In any case, let's see here. Okay, so for example, the phone in your pocket, the light in your bedroom, electric cars on the roads, computers, even the biggest machine in the world, the Large Hadron Collider, relies on this set of equations called Maxwell's equations. You'll run across these in your physics classes. I'm not sure what the number is, but it's the class on um, electromagnetism stuff. So if you take one of these things that we use, and you start asking why does this happen? Why does that happen? You keep asking why. Fundamentally, what it comes down to eventually is you'll run into these equations. These are basically the basic model for all of magnetism and electricity and how they're related. And they're surprisingly very simple. There's 4 of them. I think there was 20 at one time, and turns out a lot of them were just different versions of the same thing. So they condensed them down to 4. And pretty much these power the modern world, power electricity and magnetism. Pretty much so much stuff that we rely on relies on those things. So super powerful applications. So it turns out Stokes' theorem provides the justification for the Maxwell-Faraday equation and the Maxwell-Ampere equation and their integral forms. That's something else I'm not going to talk about, but it's the equivalent of this, an integral form. Okay, you don't need to know, the specifics of this, but when you do run across this in your physics classes, just know that the stuff that we've discussed in this section lays the groundwork for understanding these things. By the way, the other law, the divergence theorem, will help us with these two. All right, so what is Stokes' theorem? Well, essentially what Stokes' theorem is, it's an extension of Green's theorem circulation form. So I'm going to state Green's theorem once again. This is it stated again, and then I'll kind of give you the idea of what's going to happen in order to get to Stokes' theorem. We're essentially going to lift the whole situation out of the plane and into space. All right, but the idea is synonymous. It just requires some more intricate tools to understand. So Green's theorem. So here's a picture of the region R. So let's make sure R is a region in R2, right? Remember this. It's got to be a connected and simply connected region. So we've got that. And then the boundary of R has to be a closed curve, which it is. The curve has to be piecewise smooth, no sharp corners, which it is. It has to be simple. And the last thing is it has to be oriented in the counterclockwise direction, like so. Like this, in the counterclockwise direction. So if you have this set up, and by the way, the T direction would point in the direction of movement, right? And then the N direction is always to your right or outward. But anyways, if you have this set up, then this holds. This is Green's theorem. It basically says that if you take all the tiny rotations inside R, right? That's the curl at every point in R, and you were to add them all up. That's what an integral is. You add them all up across R. What happens is all the ones on the inside cancel, and what you're left with is all of the tiny rotations on the boundary, which collectively make up the circulation of the vector field on C, the boundary curve. C is the boundary of R. All right, so we studied circulation quite a bit before. All right, so that's basically what I said here. So this is important that you have, this specific kind of region so that the Green's theorem holds. So we've pretty much done all the heavy lifting of taking this and extending it up to R3 as far as the tools we need. We're going to need curl in R3. We're going to need surface integrals in R3. So the first thing we want to do is talk about we're not going to be integrating over this region. It's going to look a little different. It's going to be in R3. So what do I mean by that? Well, look, imagine you had this region R in the floor, in the XY floor. Essentially, we're going to take that region and we're going to bring it up into space. And it doesn't have to be flat. It can be like dome shaped or something like that. Or it can be just go off like a bubble somewhere. That's kind of the general idea. So, and we're going to be taking a surface integral over the surface, collectively adding up all the little curls on the surface and showing that the result is the circulation along the boundary of the surface. Okay. So let me show you a picture of our new kind of setup. This was our setup for Green's theorem. Let me show you this. Okay, so we're going to take our two-dimensional region in the floor and we kind of lift it up into space, and it can be kind of, blobby like this. But there's our surface. And you can see that this surface clearly has a boundary, which is a curve in R3. In Green's theorem, it was a curve in R2 because we were in the floor, but now the boundary is a curve in R3. So what are the conditions on this setup? Well, for Stokes' theorem, the surface that you're working with, S, it needs to be a piecewise smooth curve. So no sharp, well, you can have sharp corners as long as it's made up of, it's got to be piecewise smooth. So it needs to be made up of smooth pieces, basically. And then in addition to that the boundary curve C of your surface in blue right there, it also has to be piecewise smooth. And there's one other restriction, and that is that the orientation of the surface must be consistent with the orientation of its boundary curve. All right. So let's talk about what that means. I haven't explained that in the picture. So here's the idea. So this is a similar surface. So let's say you have a surface, an open surface like this. You remember, you have the freedom to orient it how you want. You could orient it so that the normal direction is upward, kind of outward like this, or you could orient it so the normal direction is downward. It just kind of depends, right? What you're being asked to do or what you want to do. But in order to use Stokes' theorem, it turns out that your normal direction has to be consistent with the orientation of the curve. Remember, these curves are parametric. So there's a specific direction in which this curve is being traced out. So how do you determine how to orient the surface, which direction the surface should be oriented? Well, you use the right-hand rule. So what you do is you take your hand and you curl your fingers in the direction of rotation. So that would be C, right? Kind of curling around. And your thumb will point in the direction, the normal direction, which is kind of upward or outward in this case. And this is pretty common to have the orientation set up this way, where the normal vectors point upward. It's pretty typical. I mean, occasionally you might want to cross one where C is oriented in the opposite direction and they'll point downward, but it's pretty much, when viewed from above, the curve will always be oriented counterclockwise, which means the normal vectors will point up. Okay, just so we'll kind of stick with that convention, at least for now. And I think it'll help get some consistency, and then we can change the direction later. All right, so we're going to be integrating over these three-dimensional surfaces, oriented surfaces with normal vector pointing up. So let's take a look at Stokes' theorem. We can kind of jump right in because we've already developed the tools. So if you have that set up, there's your surface. It's got to be oriented. S and C have to be consistent with each other. They're normal. They're using the right-hand rule. And let's say that your vector field F is continuous, has continuous first partial derivatives on the surface. Then what this says is that if you add up all the curls, remember integrals are sum, if you add up all the curls, and more specifically, the normal components of all the curls. Okay, remember, a curl is a vector, so you're getting the normal components of all of those curls, which is a measure of the rotation at a point on S. And you sum all those up, then it's the same thing as just looking at the boundary of S and finding the circulation on the boundary. Now, this is actually the same as Green's theorem, right? On the right. Where's Green's theorem? The only difference is this was a curve in R2, and this, the boundary curve, this curve is in R3. Okay, so the new part really is the left-hand side. This is the accumulated curls on the surface, all these little rotations on the surface. All right, and again, you have to make sure that your normal vector is pointing in an orientation. Your surface is oriented so the normal vector agrees with the right-hand rule with the orientation of C. Okay. All right. So the idea is completely the same. So I've got a little animation here, hopefully to help a little bit. We'll see if this works. Okay, so what I've got here is the right-hand side of Green's theorem, I'm sorry, Stokes' theorem, and the left-hand side, and they're equal, so you should get the same result for both. So let's start with the left-hand side. Okay, so we're integrating over a surface. So let's pick a surface right there. It's got a boundary curve C. Oh, it's not working. Okay. The surface has some parameterization. So this would be the parameter region here. So what's happening? Well, if you take any point on surface, well, let's move it over here. And you have a normal direction, which is consistent with the right-hand rule. So the normal vectors are going to point upward, right? And then you have your curl at every point on the surface. Remember, curl is a vector, and it's a measure of the rotation of the vector field on that particular surface. But when you dot that with the normal vector, the normal direction, it gives you the component of the curl in the normal direction, essentially giving you the amount of rotation at any particular point, which you could visualize with a kind of a spinning paddle wheel. And you'll notice that paddle wheel is kind of at an angle, and that's why we dot in with the curl there. So you're going to get all these different curls as you move along. Sometimes it'll move faster or slower or the opposite direction. It just depends on the vector field at that point. Okay, because you do have a vector field everywhere. And of course, we only care about the vector field on the surface. I don't know why that button's not working. Oh, there it is. Okay. All right. So we're going to add all those up, all those little curls across the whole surface. And that's essentially the left-hand side. That's the accumulated rotations on the inside at every single one of these points on the surface. Now, what's going to happen is all of the ones on the inside on your surface are going to kind of cancel each other out, and all you'll be left with is what's on the boundary. So you'll have the sum of a bunch of curls on the boundary, which is essentially the circulation, which is the right-hand side on the boundary curve C. Okay, so the circulation, well, there's your boundary curve C. It's oriented counterclockwise from above. Of course, to find circulation, you're going to integrate the vector field dotted with R prime. And as you go along, you'll have positive and negative contributions. And whatever you get for a result, when you add them all up, will be the same thing as if you did the surface integral. Okay, you'll get the exact same thing. So you might wonder, like, why would you ever use this? Well, it's a good question, right? So let's say that you're asked to do let's say you have a closed curve, and it's kind of a weird curve, and you're asked to find the circulation of a vector field on a curve. But let's say this is super hard. Maybe the parameterization of C is super difficult. It's got multiple parts, and you don't want to do all that work. Well, what Stokes' theorem says is what you can do is just find any surface whose boundary is C, maybe something like this surface here. It doesn't have to, really any surface will work. And then just add up all the components of the curl in the normal direction, and you'll get the same result. So it's possible that this might be easier than doing that. And then on the flip side, let's say you're asked to add up all the components of curl in the normal direction on the surface. And this is difficult, but the boundary curve is super easy to work with. Well, in that case, you just evaluate this. So you can kind of use it to your advantage on each end. Okay, so let's use it. In our first example, we're just going to verify that Stokes' theorem holds. I'm going to evaluate the left-hand side, and I'm going to evaluate the right-hand side, and I'm just going to show that you get the same result. So let's say that we have this this vector field here. By the way, this is a rotational vector field. There's your radial vector r, and there's your axis of rotation vector. And when you cross those together, you get this. So this is the given vector field, where this is the axis of rotation. And let's say this vector field is defined on a surface given by a hemisphere of radius 2. So that would, written explicitly, would look like that. Okay, so we're going to verify that Stokes' theorem holds. I need to tell you what the orientation on the boundary curve is, right? The orientation is going to be in the counterclockwise direction when viewed from above. That's pretty standard. Okay, so should we do this? Okay, I can show you the picture if you want. Here's the, let's look at the left-hand side of Stokes' theorem. Don't see, okay, well, that's the left-hand side right there. Okay, so normal directions point outward, right? Consistent with the right-hand rule since we have a counterclockwise orientation on C. You're basically going to take all of these guys, find the components in the normal direction, add them all up, and then see what you get. That's the accumulation of the curl everywhere on S. Now, on the other side, we're going to find the circulation on the boundary. This is just a plain old line integral. So you got to make sure to parameterize that curve. We'll talk about that. And then you're going to take the dot product of F and R prime, and that will give you essentially the component of your vector field that agrees with the forward direction of the curve, and add them all up, right? And when you do that, you'll get the same result as you did with the surface integral. All right, so that's what we're expecting. So let's go ahead and do it. If we look at the curve in the floor here, look at the boundary of the given surface, we would just set z equal to 0, and that would give us the curve, the boundary curve in the floor, which is x squared plus y squared equals 4. So we need to parameterize this. We got to make sure it's parameterized in the counterclockwise direction when viewed from above, and this works, right? It's pretty standard parameterization, one time around. And if you look at it from above, it'll be in the counterclockwise direction. It's consistent with the right-hand rule, so we're all good. All right, so we're going to do the left-hand side and the right-hand side. So let's see. The right-hand side I'm calling circulation of C, and the left-hand side I'm calling the accumulation of the curl. So let's do the right-hand side first, the circulation on C. So we did this back in 17.2. You're going to need the derivative R prime. So when we calculate the circulation, what we'll do is take F dot R prime, integrate from 0 to 2 pi. And I'll let you look through the specifics there. We've done this enough times. So we've got 8 pi. So we've got a positive contribution. I'm sorry, a net positive, what would you say? The vector field F is agreeing more than disagreeing with the forward direction of the curve. Okay. All right, so when we do the accumulation of the curl, we should, on S, everywhere on S, we should get the same thing. So let's just make sure that happens. So how do you do this? Well, first you got to find the curl. So that's fairly easy. You take nabla across the vector field F. Requires a little work here, but you end up getting 0 to 2. By the way, oh, never mind. Okay, 0 to 2. And then what else do we need? Let's see, we're going to need a normal vector. Okay, so we can look this up in the table because we have a hemisphere, which is part of a sphere. There it is. You got to make sure it points in the right direction. The z component is positive, so that it's pointing in the right direction. So we don't need to negate it or anything. And then we'll set up our accumulation of our curl there. All right, we'll just plug everything in. This is nabla cross F. There it is. Right there. We computed that here. And then we'll dot that with N. And we'll be integrating over the region R. Let's see. By the way, we're doing this explicitly, right? There's no U's and V's in here. When we take the dot product of those two things, we get this guy. We've got a little bit of an issue. We've got a Z there. Remember, everything needs to be in terms of X and Y. The region R is in the XY plane. But that's an easy fix. We'll just take Z and replace it with, where's Z? We'll solve this guy for Z and we'll replace it with this guy. Okay, so now you got everything in terms of X and Y. You're probably going to want to convert to polar. Definitely, the region of integration is this shape. You know, this kind of suggests polar, so we'll convert to polar. I'll let you guys work through the specifics there. But you do indeed get 8 pi. Okay, so we've confirmed that Stokes' theorem holds. Okay, it will always hold as long as you satisfy the requirements of a theorem. That's what theorems are. They don't break, right? They're proved to be true once and always. Okay, so let's dig in a little deeper. Let's actually this time, let's use Stokes' theorem to evaluate a line integral. And what I mean is we're going to use the other side of Stokes' theorem. So we're going to do the line integral. By not doing the line integral, we're going to do a surface integral. That's what Stokes' theorem does. It gives you an alternate way to do the problem. So here's our vector field. I don't need to show you the whole thing, right? But that's a vector field. So, and then let's see. We want to find the circulation of the vector field along C, where C consists of the line segments that bound this plane. So this plane would be that plane in blue right there. And we're restricted to the first octant, so that way it has an edge. And we're orienting it kind of like so. So if we were looking at it from above, this would also be in the counterclockwise direction. So this is a standard orientation. So let's say you wanted to find the line integral along this boundary. So the first question would be, why don't we just do this directly? Let's do the line integral along the boundary. And there's kind of a immediate thing that's probably coming to your mind, hopefully, and that is that would really suck, right? Because you've got to parameterize 3 curves, 1, 2, 3, because it's piecewise smooth, right? So you got to do 3 separate curves. And then you got to do 3 separate integrals, 1 for each curve, and that's just such a pain. So why don't we use Stokes' theorem, right? That's gonna be much easier. All right, so how do we use Stokes' theorem? Well, remember the other side of Stokes' theorem says if you want to evaluate the circulation, you can just instead find the accumulated curl on the surface inside. Now, the surface that we're going to use is going to be the plane. By the way, it doesn't have to be the plane. It just has to be anything with C for a boundary. But I think using the plane is probably about as easy as we're going to get. And we might as well choose the easiest surface possible. So, but it doesn't have to be. You'll still get the same result, right? All right, so let's see. This is given, let's see. We're going to do this explicitly. Okay, so let's find the curl of F. We find nabla cross F. There's nabla cross F. Go ahead and evaluate, and there's our curl vector. All right, now you're going to want to find the ZX. You're going to want to find a normal vector to the surface. So to find that, you could just use this. Remember, we did this for explicit surfaces. I showed you that above in that theorem. It's just negative ZX, negative ZY1, or positive ZX, positive ZY, negative 1. Try one and find ZX, find ZY. That's fairly easy to do there. Plug them in and then make sure that it's the correct direction. So in this case, the Z component is positive. So let's make sure. So that would mean it's pointing upward more. So this would be the normal direction indicated by this guy, or close enough, it's pointing upward. And then make sure that it satisfies the right-hand rule, which it does. So we don't have to negate this thing. It's good to go. So we're going to use that guy. Now, since we're doing this explicitly, we're going to be projecting the surface onto the floor. So we need that region R. You can do that now or later, but it's going to end up being a triangle. I'll let you guys figure that out. We've done so much of that stuff. So hopefully you know how to do that. So let's evaluate the circulation. That's what we were asked. So rather than do it directly, we're going to use Stokes' theorem. So I'm replacing it with this. I found the coral. That's this guy. And there's the normal vector. I'll dot them together. Simplifies to this. And then I'll just evaluate over the region R, which was that triangular shaped region. If you run through and do the math there, you'll end up getting -88/3. So the circulation is negative. So what does that mean? That means that as we move along the boundary curve, the curve C, in the forward direction, that means that more of the vector field disagrees with the direction of C than agrees with it. The vector field is working against us as we move along this thing. Okay? All right. I'm not showing you the vector field. You just kind of have to imagine that. All right. Guess that's it. Yeah, this is just a note. You can leave that out. Okay. Yeah, keep in mind, I don't know if I mentioned this, but these guys are flux integrals, right? It's how much of a vector field passes through a surface. But we're not using an F there. We're using a nabla cross F. And what that does is it turns it into a curl. We don't really have a name. We don't call it a curl integral, but it turns it into finding the accumulation of the curl on the surface. Okay, so be careful there. All right, two more. Let's see. Let's evaluate this surface integral. That's the accumulation of the curl on the surface, and then we've got our vector field here. And in this case, our surface is going to be part of this paraboloid. That would be the upside down one right here. That lies within this paraboloid, opens upward. That's going to be this orange one there. And all we care about is part of this, but inside. So that's going to be this region in blue right here. And we're going to orient that surface in blue. We're going to orient it so that the upward direction is normal. Okay? All right, so we're just looking at the surface in blue. You can ignore that orange, everything else if you want. All right, so we're going to find the accumulation of the curl everywhere on that surface. All right, so here we go. If we're going to use Stokes' theorem, of course, one way to do it is to parameterize your surface and calculate a surface integral. But I don't want to do that. This surface is pretty ugly to parameterize. I'd rather not do that. So let's use the other side, the circulation side of Stokes' theorem. And that's going to require a curve. So this is going to be our curve. We're going to go around that. Oh, it works now. Right around that curve and back up on this side. We got to come up with a parameterization of that curve, and then we'll just find the circulation on that curve. So that's a little tricky, but not too bad, right? How do you parameterize that boundary between the intersection of those two surfaces? Well, we do know that at the intersection, we know that both of these things must be true. You have to be on both paraboloids. And if we were to eliminate z here, what we can see is that x squared plus y squared equals 1. Essentially, if you looked at their shadow onto the floor, it'd be a perfect circle of radius 1. So we definitely have the x and y components of our parameterization. But what we don't have is the z component of our parameterization. So, but that's fairly easy to get because, it has to satisfy both surfaces. So pick one and then just plug in your x and y values. Your x and your y values in. It doesn't matter. You could pick this one too, but I picked this one, and just use that for your z component, and you're good to go. We're going one time around the circle. from 0 to 2 pi. And then you probably want to just make sure that it's oriented, how you want it oriented. Since the normal vector is chosen to be upward, we got to make sure this thing C is oriented in the counterclockwise direction when viewed from above. Hopefully you can see that because the cosine t is first and the sine t is second, that ensures that we go in the counterclockwise direction. If you wanted it to reverse, you could just switch the sine and the cosine and the sine and the cosine. Okay, so we're good to go. Okay, so here's our vector field. So we're going to end up calculating this line integral, right? Instead of doing the, oh, I put flux. That shouldn't have been flux. That's the accumulation of curl. Okay, so rather than do the accumulation of the curl, we're going to do the line integral. So you're going to need f dot t. So sometimes I'll do the workout here. Here's f. You're going to need r prime. When you take f dot r prime, you end up getting this thing. It's a little bit ugly, but you're just going to plug that in, evaluate from 0 to 2 pi. A lot of this drops out. These guys are 2 pi periodic. That guy's 2 pi periodic. Since you're integrating from 0 to 2 pi, these guys drop out. So you're just integrating the one function from 0 to 2 pi, which is 2 pi. Okay, so we've got a positive answer. So what that means is, let's see, we were asked to find the accumulation of curls. So that means that if we add up all the curls on this surface, the net result is a counterclockwise direction because we got positive surface integral there. Okay, some of them might rotate the other way, but the net result, there's more that are rotating in the counterclockwise direction. All right, okay. By the way, it also means that the circulation on the boundary is positive. So that means the vector field agrees more than disagrees with the forward orientation of the boundary curve. And lastly, let's use Stokes' theorem to evaluate another surface integral. So this is going to be similar to the one we just did. And notice I'm evaluating the same surface integral. I think it's the same vector field. Yeah, same vector field. Same paraboloids. But in this case, we're looking at a different part. So it's going to be part of the bottom paraboloid, but lies within this one. So now we're looking at the orange region down here. This guy down here. We're going to assume S is oriented. So that's S now, right? The orange region. We're going to assume that that region is oriented upward. So I don't know if you can see it right there, but it's this one. It's oriented in the upward direction. And then we're going to ask and then after we're done, we'll ask yourself what you think, how would this affect the surface integral if we had oriented n downward? So, but we'll get there. For right now, we'll assume it's oriented upward. And here we go. Now, here's the thing. This is actually really easy. This is essentially pretty much the same setup as the last problem, right? Stokes' theorem says that the circulation on the boundary is equivalent to the accumulated curl on the surface, no matter what the surface is. And as long as you're oriented, so that means that as long as you're oriented in the same direction and you have two surfaces, they have to get the same result. So if you notice, the blue surface and the orange surface are oriented in the same direction, right? Their normal vectors point upward, but they have the same boundary curve, which means the circulation has to be the same. In other words, the right side of Stokes' theorem is the same for both of them, which means their left sides have to be the same. So you really don't have to do any work here. You already know the answer. So if you were asked to find the surface integral along this different surface, it necessarily has to be the same answer. It still has to be 2 pi. Now, if you want, you could run through the calculations and you'll get the same answer. Okay. Now, the last part is, what if we were oriented the orange surface so that the normal vector pointed downward? How would that change things? You can probably guess, instead of getting 2 pi, you'll get negative 2 pi. You might want to go through the reasoning. If it was oriented downward, we'd have to change our orientation of our curve so that the right-hand rule works. So we'd reverse the first two coordinates, that would be sufficient. This would make it rotate in the clockwise direction. But all of the work would be very much the same. And if you ran through and did the calculations, you would get negative 2y. Okay? All right. By the way, we've been talking about open surfaces. What about closed surfaces? What if I wanted to find the surface integral? What if I wanted to find this guy on this entire surface, right? The blue and the orange surface. Let's say this was one big surface. What would the result be there? What would the accumulation of all the curls be? Well, what would end up happening is essentially everything would cancel out, right? Because you have positive 2 pi on the top and negative 2 pi on the bottom. So what ends up happening here is the surface integral over both surfaces, if it's closed, necessarily has to be 0. In fact, I think I talk about that here. Like if you have two surfaces and they have the same boundary curve, then by Stokes' theorem, you're going to have to get the same result, right? Because their circulation's the same. The line integral and the boundary is the same. So that means these must be the same. And then you can imagine if you took the whole surface and put it down into this like egg-shaped thing and you oriented ends so everything was pointing straight outward, then, you know, one of these would be positive and the other would be negative, but they'd be the same magnitude. So what would end up happening is, you know, if you were to go across the whole surface, you would add the integral across S1 plus the integral across S2, but S2 would be the negative of S1. So you're essentially just adding and subtracting the same surface integral, and you'll always get 0 no matter what. Okay, in other words, if you've got a closed oriented surface and you want to find the accumulation of the curl, you will always get 0. All right. Okay, and the last thing just to mention here, we kind of skipped over this or maybe assumed it before. You might already know this, but we didn't actually prove it. But look, if F is a conservative vector field in 3 dimensions, that essentially means, I mean, we already showed this, that the curl of F, nabla cross F, will always be the 0 vector. And that essentially means that the vector field is irrotational. There's no rotation anywhere. Okay, that's what it means for a vector field to be conservative. So by Stokes' theorem, now we can say, okay, let's compute the line integral, the circulation on any boundary, on any curve C that's closed. Well, by Stokes' theorem, that's equal to the accumulation of the curl on any surface whose boundary is C. And since for conservative vectors, the vector fields, the curl is 0, we can put that in, dot that with any normal vector, you're going to get 0. You're integrating the 0 function, which is 0. So that means that the circulation along any closed curve for a conservative vector field will always be 0. Okay, so we talked about those equivalences in the past few sections with conservative vector fields, right? Vector fields conservative if, you know, there exists a potential function. Line integrals are path independent. We said this one too. Line integrals on closed curves are 0, and the curl is 0. So essentially, this kind of proves the last remaining part we hadn't proved before. All right. Okay, and we're going to skip over this part. I don't think I gave you any homework, and I'm not going to ask anything about it, but it is interesting if you want to take a look.